Good morning, student. Myself, Kausik Chakraborty. In my previous video lecture, we discussed about the working principle of ring counter and Johnson counter. Today, we discuss the synchronous counter. We all know synchronous counter are counter in which all the flip-flop are triggered simultaneously by the clock input pulse. Since all the flip-flop change the state simultaneously in synchronization with the clock pulse, the propagation delay of flip-flop do not add together to produce the overall delay. Next, advantage and disadvantage. Advantage. Synchronous counter have the advantage of the high speed and less server decoding problem. Disadvantage. Design and implementation became complex as the number of states increase. Design of synchronous counter. For a systematic design of synchronous counter, the following 5 procedure is used. Step 1. First, we have to look at the question to understand how many flip-flop we need. Step 2. State diagram. Draw the state diagram showing all the possible state. Step 3. Choice of flip-flop and excitation table. Select the type of flip-flop to be used and write the excitation table. Step 4. Minimal expression or for excitation. From the excitation table, we will create the equation with the help of K-map. Step 5. Logic diagram. Draw a logic diagram based on the minimal expression. The excitation table of the various flip-flop used in the counter. This is the excitation table of SR flip-flop. This is the JK flip-flop. This is D flip-flop, and this is T flip-flop. First, SR flip-flop. When present state value 0, next state value 0, this time S value 0, R value cross. Present state value 0, next state value 1, this time S value 1, R value 0. Present state value 1, next state value 0, this time S value 0, R value 1. Present state value 1, next state value also 1, this time S value cross, R value 0. Here cross means don't care. Next is JK flip-flop. Present state, next state, both values 0. This time J value 0, K value cross. Present state value 0, next state value 1. This time J value 1, K value cross. Present state value 1, next state value 0. This time J value cross, K value 1. Present state, next state, both value 1. This time J value cross, K value 0. Next is D flip-flop. Present state, next state, both value 0. This time D equal to 0. Present state 0, next state 1. This time D1. Present state 1, next state 0. D equal to 0. Present state, next state, both state value 1. This time D value 1. Next is T flip-flop. Present state, next state, both values 0. This time T 0. Present state 0, next state 1, T value 1. Present state 1, next state 0, T equal to 1. Present state 1, next state 1, this time T value 0. This is the one example. Like design a synchronous 3-bit up counter using JK flip-flop. Step 1. Determine the number of flip-flop required. A 3-bit up counter required 3 flip-flop. The counting sequence is 000, 001, 010, 011, 100, 101, 110, 111, again return to 000. Step 2. Draw the state diagram. At first, we start the counting 000 state. So, this is the state diagram. This is 00 state. We start counting here. So, the next step is 001. Next 010. Next 011. Next 100. Next 101. next 110, next 111. Again return to 000. Step 3. Select the type of flip-flop and draw the excitation table. JK flip-flop are selected and the excitation table of 3-bit up counter using JK flip-flop is drawn in shown in this figure. This is the JK flip-flop excitation table, and this is the problem excitation table. This is present state, this is next state, and this is input. Here we use the 3 flip-flop, that's why Q2, Q1, Q0 in present state, next state also Q2, Q1, Q0, and 3 flip-flop is J0, K0, J1, K1, and J2, K2. First we look the state diagram. We start counting in 0, state, that means here. So this is the present state, that's why we put the value in present state 0, 0, 0. So the next state is 0, 0, 1. So the next state 0, 0, 1. Next step 0, 0, 1 is the present state. Okay, 0, 0, 1 is the present state. So the next state is 0, 1, 0. That's why 0, 1, 0. Next step 0, 1, 0 is the present state. The next state is 0, 1, 1. Next step 0, 1, 1 is the present state. This time next state is 1, 0, 0. Next step 1, 0, 0 is the present state. Next step is 1, 0, 1. Next step 1, 0, 1 is the present state. The next state is 1, 1, 0. Next step 1, 1, 0 is the present state. Next state is 1, 1, 1. Next step 1, 1 is the present state. Next state is 0, 0, 0. Okay, with the help of JK excitation table, I will create the excitation table of the problem. I will create the excitation table of the problem. When we find the excitation table of J0, K0 flip-flop, we need to work on the present state Q0 value and next state Q0 value. So this is the present state Q0 and this is the next state Q0. At first, present state Q0 value is 0 and next state Q0 value is 1. Go to the truth table, present state value 0, next state value 1, this time J value 1 and K value cross. So J value 1, K value cross or D. Next, present state Q0 value 1, next state Q0 value 0. Go to the truth table, present state Q0 value 1, next state value 0, this time J cross K 1, this time J don't care or cross and K 1. Okay, so we will extract the remaining value of J0 K0 flip-flop in the same process. Next is J1 K1. So when we find the excitation table of the J1 K1 flip-flop, we need to work on the present state Q1 value and next state Q1 value. So the present state Q1 value is 0. Next state Q1 value is also 0. Go to the truth table, present state 0, next state 0, this time J value 0 and K value don't care. J value 0 and K value don't care. Next, present state Q1 value 0, next state Q1 value 1. This time the this time the value is 1D. We will extract the remaining value of the J1 K1 flip-flop in the same process. Next is J2 K2. When we find the excitation table of J2 K2 flip-flop, we need to work on the present state Q2 value and next state Q2 value. So present state Q2 value is 0. Next state Q2 value is also 0. That's why the J2 value is 0 and K2 value D. Next, present state Q2 value 0. Next state Q2 value 0. That means again J0 value, J2 value 0 and K2 value D. So we will extract the remaining value of J2K2 flip-flop in the same process. Next step is K-map. This is a 3-variable K-map. We all know the 3-variable K-map procedure. This is the J0 K-map. Here we put all J0 values. This is one combination. That's why J0 equal to 1. This is a K0 K-map. This is one combination. That's why K0 equal to 1. This is J1 K-map. This is the combination. That's why J1 value equal to Q0. This is K1 K-map. This is the 4 combination. That's why K1 equal to Q0. This is J2 K-map. This is 2 combination. That's why J2 equal to Q1 Q0. And this is the K2 K-map. This is the combination. The equation is K2 equal to Q1 Q0. This next is circuit diagram. We have draw the following circuit diagram using the above equation. Here we use 3 JK flip-flop, J0 K0, J1 K1, J2 K2, and we also use the 3 negative clock pulse. These 3 negative clock pulse is connected each other. This point is clear and this point is preset. Both are connected. So at first we see the equation J0 and K0. Both are 1. That's why J0 and K0 are connected and the value is 1. Next, J1 value is Q0 and K1 value is also Q0. So Q0 is connected to J1 and K1. Next, J2 value is Q1 Q0, means use AND gate, and K2 value is Q1 Q0, means use AND gate. So Q0 and Q1, both the input is AND gate and the output AND gate is connected to J2 and K2. Q2 bar is the output. Next, I give you a question that you try yourself. At first, you read the question properly. Design a synchronous 3-bit down counter using JK flip-flop. I am a small help to solve this problem. At first, you start the counting 0 0 0 state, means initially the 3 flip-flop value is 0 0 0, means 0 0 0 is the present state. That time next state is 1 1 1. Next step 1 1 1 is the present state. This time next state is 1 1 0. Next step 1 1 0 is the present state. The next state is 1 0 1. I think you are understand my hints. So you solve the problem, and thank you.